All right, so just a reminder with the work energy theorem problems, okay, write down your givens, decide whether it's potential or kinetic energy, okay, set up work energy theorem, okay, force times distance, change in energy, okay, manipulate and solve. All right, give you a few minutes to try that one there. Okay, so if we're reading this through, we got a rubber band, okay, and it's used to shoot this marble. They give us the mass of the marble, okay, so that's handy, we'll need that. Okay, 0.135 kilograms along a level floor. Okay, anytime I see the word level, it's telling me what's not changing. Height. Yeah, if it's level, the height's not changing. So more than likely, this is a kinetic energy question. Okay, the rubber band is stretched using 300 newtons. Okay, that's force. So I've got that. Okay, and the marble starts from rest, so VI is 0 meters per second, and reaches a speed of 18 meters per second. Okay, so definitely a kinetic energy question because I do have changes in speed here. Okay, we're looking for how far was the band stretched? That would be d. All right, so in this question, the work being done is changing the kinetic energy of the marble. All right, next step, expand this out. I have force, I'm looking for distance, and I'll have 1/2 mvf squared, my final kinetic energy, minus 1/2 mvi squared, my initial kinetic energy. What is my initial kinetic energy? 0, because it said it started from rest. It didn't have any kinetic energy initial. So I can just get rid of that. That's going to make my life even easier. I'm just solving for d. What do I have to do with f? Divide it over to the other side. Okay, so that means that d will equal 1/2 times 0.135 times 18 squared divided by 300 newtons. Okay, so 0.5 times 0.135 times 18 squared, okay, divided by 300 newtons. Okay, so we didn't bring the rubber band back very far. That's 7.3 centimeters. Okay, so yeah, about like that. Okay. I mean, it's enough, right? It launched the ball. Okay, so we would write just 0.073 meters probably. Okay, questions on that one? Okay. All right, let's give that one a try. That's a little bit more involved than the last one, okay, but not terrible. All right, so in this one, they tell us the mass of the sprinter. Okay, so we got 75 kilograms there. They also tell us how much force the sprinter can exert, 225 newtons. Okay, and it says that over the last 10 meters of their race, meters measures distance. Okay. Okay, they increase their speed from 14 to their maximum. That means 14 is initial or final? Initial. All right, we're looking for their maximum / final speed. All right, obviously then we've got work changing the kinetic energy of the sprinter, okay, because there's only mentions of changes in speed here. We have both force and distance, okay, and then we have 1/2 mvf squared, and that's what we're looking for is the vf, okay, minus 1/2 mvi squared. Okay, since I have the m and the vi, can I move that whole term, 1/2 mvi squared, over to the other side to help me isolate vf? Okay, how would I do it? Right now I'm subtracting, so to move the whole thing I would add it over to the other side. Okay, so what I'll have over here, after I add 1/2 mvi squared, it'll cancel here. Okay, what I'll have is work which is a change in energy, plus the initial energy equals the final energy. Okay, that should make sense. Whatever energy I start with plus the change should equal what I have at the end. Okay, I still have to get VF by itself. What do I need to do with the half and the m? Right now I'm multiplying 1/2 times m times VF squared. So if I want to move the half and the m over, I need to divide. Right. Okay, so that's going to come over here. Okay, usually at this point people are like, doesn't that cancel? I got it on the top and the bottom. The answer is no, it doesn't, because you're adding on the top. If everything on the top was multiplied, then yes, you could cancel, but here you can't. Okay, now that gets me VF squared. I just want normal VF, so what do I need to do? Square root the whole thing. Okay, they don't get more involved algebraically than that question. That is the most you will ever have to do in a Science 10 work energy theorem question. Okay, we'll take our force, 225 newtons. We'll multiply that by the distance, 10 meters. We'll add to that 1/2 times the mass, 75 kilograms, times the initial speed, 14 squared. Okay, divided by 1/2 times 75, all square rooted. That will give me VF. 225 times 10. Okay, plus 0.5 times 75 times 14 squared. Okay, divided by the bottom, 0.5 times 75. Okay, then I got to square root that. Okay, so over the last 10 meters, they accelerate from 14 to 16 meters per second. Okay, that makes their maximum speed 16 meters per second. Okay, questions on that one? Okay, as I said, that's the hardest you could ever expect to see. Okay, let's try this one. Okay, so we're looking for the height that this arrow will reach if it was fired straight up in the air from the ground. So kind of like the question we did the other day where the person was lying on their back on the ground and had drawn back. Okay, so that's what they're doing here. Okay, 300 newtons of force, 0.75 meters. Okay, so we're looking for the height it will reach. That would mean probably the final height, especially since they do define the initial height as on the ground, where the height would be 0 meters. All right, we also know the mass, okay, 0.09 kilograms, so 90 grams. Okay, it's fired straight up in the air. The force is 300 newtons. Okay, and the distance the draw is drawn is 0.75 meters. All right, we are talking about a change in potential energy here because we're talking about a change in height. So force times distance, m times g times h final, minus m times g times h initial. Since h initial is 0, this part becomes irrelevant. Okay, and I'm just solving for hf. Since I'm multiplying these three things together, if I want to isolate hf, I just divide both sides by m times g. All right, so hf will be 300 newtons times 0.75 meters over 0.09 kilograms times 9.81 meters per second squared. Okay, so it's going to reach a height of 254.84 meters. Okay. Questions on that one? Is it okay with that? Okay, give this one a try. We haven't done a ramp one in a while. Okay, 1.2 kilogram ball is rolled up a ramp at a constant speed. Okay, how much force is required to get the ball to the top of the ramp? Okay, so the top of the ramp is 8.2 meters above the bottom of the ramp. Assume we're starting at the bottom. Okay, so we'll change the height by 8.2 meters, and we'll push the ball 22 meters along the ramp. Okay, give you a few minutes on that. All right, so we know the mass. Okay, they gave us the 1.2 kilogram ball. Okay, the 22 meters is going to be our distance. The 8.2 meters is going to be our final height. Our initial height is obviously going to be 0 because we're starting at the bottom of the ramp. Okay, we are looking for how much force is required. Okay, and this is the kind of question that illustrates why the inclined plane, the ramp, okay, is the simplest machine. Okay, it makes work easier. Okay, is it less work to roll something up to the top of the ramp or to lift it up? Or is that a trick question?
Roll.
Okay, seems like it should be roll, like that would be less work. But here's how I would word that if I was making it a question on an exam. Okay, I would say it just like that. I would say, which is less work? And people confuse work with force. If I get the ball to the top of the ramp, whether I roll it up the ramp or I lift it there, I change its energy, which is work, by the same amount. But it's easier to roll it up the ramp because I don't have to exert as much force. That's the purpose of the ramp. But because we associate what we're doing, okay, like the ease of rolling it versus lifting it with the work, we get that definition confused. Okay, and it's a very common thing. Okay, it's a very easy thing to get confused because it's like, well, I'm doing less work because this is way easier. Well, actually, you're not. Okay, remember that work is force times distance. If I lift the ball from here to here, I use more force over less distance. If I roll it up the ramp, I use less force over more distance, but I change the energy of the ball by the same amount regardless of how it gets there. Okay? That's why ramps make work easier, not less work. Physically speaking, there's no way to make getting a ball to the top of that ramp less work. I have to change the energy of the ball by X number of joules no matter how I do it. Okay? It's how I do it that can make it easier, not less. Does that make sense? Okay, it's an important distinction, right? If you don't understand that, you will be an inclined plane wrapped around an axis. That's a screw. An inclined plane wrapped around an axis is a screw. You'll be screwed if you don't understand that. It's a Sheldon Cooper joke. It's also true. That's what a screw is. Okay? It's a ramp, but you wrap it around the middle of the nail. It's easier to get it into the wood. Okay, let's finish this one off. Work is a change in potential energy. It does specify we're not changing the speed here. Okay? Force times distance equals m times g times h final minus m times g times h initial, which is 0. Okay? Because we started at the bottom of the ramp. Okay, we are simply looking for force, so we divide both sides by d. Okay, F will be 1.2 times 9.81 times 8.2 divided by 22. All right, 1.2 times 9.81 times 8.2, okay, divided by 22. All right, so I only have to use 4.39 newtons worth of force to roll it up the ramp. To lift it, I would have to use 11.78 newtons because I'd just be picking it right up. Okay. All right, questions on that? Okay, I'm going to give you about a 3-minute break. Get up, walk around. talk to your friend for 3 minutes, and then we're gonna move on to conservation of energy here. So basically the remainder of the unit, except for a few minutes talking about efficiency when we come back from Christmas, okay, the law of conservation of mechanical energy will be the last thing we cover, right? It is a crucially important concept that goes hand in hand with work energy theorem. Okay? I always tell people as a physics teacher that these are the two most important concepts in physics. Okay? Because nothing happens without energy. And we need to know what happens to energy when it is transferred or changed or transformed, okay, from one form to another, from one place to another, when it's used to do work, things like that. Okay? So the first thing we have to cover is what is mechanical energy. Okay? We've been doing work energy theorem problems, and we've been writing that work is a change in energy. But we've only been dealing with either potential or kinetic. The reality is, the definition of work is that work is a change in mechanical energy. Okay? We just don't do any problems in Science 10 where we deal with a change in both potential and kinetic energy at the same time. But truly speaking, work is a change in mechanical energy. Okay? An object's mechanical energy is the sum of its kinetic and potential energies. Okay? So since kinetic and potential energy are so closely related, okay, they are combined as mechanical energy, which we abbreviate as EM. Okay? Mathematically, that looks like this. You can calculate mechanical energy by adding an object's kinetic and potential energy together. Okay? Mechanical energy is like your total energy. That means it is possible for an object to have both kinetic and potential at the same time. Right? So if you're throwing a ball to somebody, as that ball travels through the air, it is both above the ground and has potential energy and moving, and thus has kinetic energy. Okay? You add those two amounts together and you've got the ball's total mechanical energy. Okay? Most objects, most of the time, will have at least some form of potential and some form of kinetic energy. Okay, so if we're talking about throwing a ball through the air, okay, that could be like this sample problem right here. All right, so if I have a 300 gram or 0.3 kilogram baseball and I just throw it in a straight line, okay? It's 2.5 meters above the surface of the earth. It's moving at 20 meters per second. Does it have both kinetic and potential energy? Okay, do we have formulas that help us calculate both of those energy types? Okay, so calculating mechanical energy is pretty straightforward. All we do is use the formulas we've already been using in work energy theorem. We just calculate, okay, here's its kinetic energy, here's its potential energy, and I add them together, and I've got the mechanical. Okay? So for this particular situation then, that would be 1/2 times the mass times the speed of the ball. Okay, so 1/2 times 0.3 kilograms times 20 squared. There's the kinetic energy. Okay, and then the potential energy, 0.3 kilograms times 9.81 times 2.5 meters. Okay, Put those two together, I've got 60 joules of kinetic, 7.36 joules of potential. Okay, gives me 67.4 joules or 67.36 joules of total mechanical energy. Everybody okay with that? Pretty straightforward thing to do, right? All right, I would like you guys to try 8, 9, and 10. It just uses what we just did with the baseball. Okay, so the formulas you're going to use, the kinetic energy formula, okay, the potential energy formula, and this. Mechanical energy equals kinetic plus potential. Okay, let's just do 8 for now. You guys try number 8, and then we'll walk through it together just to kind of see how it works. Okay, there's one trick in that question. I give you the mass in grams. What does it need to be in kilograms? Okay, that is something you have to watch for. Okay, we have to have mass in kilograms because a joule is a kilogram meters squared per second squared. So you can't use grams or we're finding thousandths of a joule. All right, so for number 8, okay, we want to use obviously this formula because we're trying to find the mechanical energy. But to get to that, I also have to use these two formulas. I have to calculate the kinetic energy of the seagull and the potential energy of the seagull. All right, so what that's going to amount to then is that we'll have the mechanical energy being 1/2 times the mass, 0.3 kilograms, okay, times 8 squared. Okay, so there's the kinetic energy of the seagull plus 0.3, the mass, okay, times 9.81, gravity, times, 30 meters above the ground, so times 30. Right? If I punch that in, I should get 97.89 joules. So 0.5 times 0.3 times 8 squared plus 0.3 times 9.81 times 30. Okay, 97.89 joules of mechanical energy. Some of it kinetic, some of it potential. Okay. Let's have you try number 9. Number 9 wants you to find the potential energy of the athlete, okay? But it is telling you their mechanical energy. So it's giving you this number and asking you find the potential, all right? So you're not going to be using, spoiler alert, that formula to answer that question, okay? All right. Now, 3.00 times 10 to the 3, how many is that? 3,000. Yeah, okay. Remember, that little exponent there says move the decimal to the right 3 spots, so that would be 3,000 joules. Okay, so you have 3,000 joules of mechanical energy to start. All right, give you a minute to try that one. Okay, so let's have a look at this one. In this one, they give us the mass. Okay, they tell us the jumper is 55 kilograms. They tell us the mechanical energy is 3,000 joules. Okay, and they also tell us the speed, 8.33 meters per second. Okay, if mechanical energy is the sum of an object's kinetic and potential energies, and that question wants me to solve for potential energy. What do I need to do with kinetic energy? If I want to isolate EP, what do I do with EK? Subtract it over to the other side, right? This is what they want me to solve for. How much potential energy do they have? So I'm going to isolate it. I'm going to go mechanical energy minus kinetic energy equals potential energy. Okay. Well, I know that the mechanical energy is 3,000 joules. And I also know that kinetic energy is 1/2 mv squared. And I have both of those numbers. I know the person's mass is 55 kilograms, and I know they're moving at 8.33 meters per second. So, sorry, I have a plus there. I should have minus there. Minus 1/2 times 55 kilograms times 8.33 squared. All right, that should give me their potential energy. Okay, so 3,000 minus 0.5 times 55 times 8.33 squared. Okay, so that's how much potential energy they have. 1,091.81 joules. Okay, now, if this were me, this would be my part B to this question. Calculate for me how high above the ground they are. Okay, you just calculated their potential energy to be 1,091.81 joules. You know their mass. Calculate for me how high above the ground they are now. All right, so the second part of this requires a little bit of a kind of logic leap, let's say. Okay, this number that we just calculated, that is the potential energy. Okay, so our potential energy is 1,091.81 joules. Does that equal the mass of the jumper times gravity times the height of the jumper? Right? That's the formula for potential energy. So that number should equal m times g times h. Can I isolate h? What do I have to do with m and g? Divide them over. Okay, so since I know what m is, they told me that the athlete's mass was 55 kilograms. Okay, what I'm doing is going h equals 1,091.81 joules divided by 55, mass of the jumper, times g, 9.81. When I do that, I should get just over 2 meters. Okay, 2.02 meters. Did we have to do anything like that we haven't done before to do that second part? We've done tons of questions where we said EP equals m times g times h. Okay, this is asking you make the leap and apply it to something new, right? Okay, write down and try number 10. It's very similar, except it's dealing with kinetic instead. Okay, so write number 10 down, okay, and give it a try. Still EM equals EK plus EP, okay? You're just solving for kinetic this time. Okay, so let's look at number 10. We know the mass in number 10, okay? We know that the mass is 2.00 kilograms, okay? The hammer is 50 meters above the ground, okay? And has a total mechanical energy of 1,880 joules, okay? We are trying to find the kinetic energy of the hammer, all right? So we know that mechanical energy equals EK plus EP. Right? If I want to find EK, what do I have to do with EP? Right? What do I have to do? Subtract it over the other side, because right now I'm adding it. So I'll have that the total mechanical energy minus the potential energy will equal the kinetic energy. Do I have enough information to calculate the potential energy? I got mass, I got height, and I got gravity. Okay, so yes I do. So I'm going to go 1,880 joules, the mechanical energy the question gave me, minus 2 kilograms times 9.81 meters per second squared times 50 meters. Okay, if I do that operation, that should tell me the kinetic energy of the hammer. Okay, so we got 899 joules worth of kinetic energy in the hammer. Everybody okay with that? Okay, part B. How fast is the hammer falling? Okay, you now know the kinetic energy of the hammer. Tell me how fast the hammer is moving. So if I've just done this work to calculate the kinetic energy, and I know it's 899 joules, does kinetic energy also equal 1/2 mv squared? Okay, I know the mass, I know the energy, I can find V. All right, so if I want to find V, okay, what I'm going to do is divide both sides by 1/2 of m, just like we did in our work energy theorem questions, and then I'll square root, and that will get me V. So I'll have the square root of 899 joules divided by 1/2 times 2 kilograms. So basically the square root of 899, which should come out to 30 meters per second. Okay, or pretty close to 30. 29 point something, probably 29.999. Everyone okay with that idea? Okay, again, we're not using any new formulas. We're using them in a different way, okay, but we're not using anything new. Everyone okay with that idea? Okay. Now, let's say we've got this situation here. So I've got this volleyball, okay, and I'm holding it 2 meters above the ground. Okay, does it have energy? What kind? Right, it's got potential energy. Could I calculate how much? I could, okay, in fact, let's just do that, okay. Mass of the volleyball is 270 grams, okay. We know G, 9.81 meters per second squared, okay, and I said I was holding it 2 meters above the ground. Okay, so potential energy is m times g times h. Okay, got to convert that to kilograms, so 0.270 times 9.81 times 2 meters. Okay, so ball, when I'm holding it out 2 meters above the ground, has 5.3 joules of potential energy. Okay, everybody okay with that? It's not very much, is it? No, I mean, there's not much to it. It's a pretty lightweight ball. Okay, now if I drop it, okay, just let it go, obviously it falls to the floor. Okay, how much energy does it have right before it hits the floor? Okay, so ball's on the floor. I pick it up and I move it to here. What have I done? Work. How much work? 5.2479 joules, 5.3 joules worth of work, okay? Because I lifted the ball. I gave it that much potential energy. That means that's how much work I did. If I drop it, does it get any more energy? Does it lose any? Assuming there's no air resistance, let's pretend there's no air resistance. Okay, when it falls, does it lose any energy? Okay, so how much energy does it have when it hits the floor? 5.2974 joules. Okay, it's just gone from being potential to being kinetic. Right? When it's just about to hit the floor, its height is now 0. Okay? But it's moving very fast. Well, okay, not very fast, but it's moving. Okay? And so it would have just kinetic energy at that point. Okay? And all throughout the fall, the potential energy is getting smaller and the kinetic energy is getting bigger. In fact, they're just converting into each other. That's the law of conservation of energy. Okay? The law of conservation of mechanical energy says energy can't be created and it can't be destroyed. Okay? So when I drop the ball, its energy has to be conserved. Doesn't mean it has to stay in the same kind. Okay? If I drop it, it obviously loses potential but gains kinetic. It converts one to the other and conserves that energy. Now, after it hits the floor, okay, that energy is still conserved, but it's no longer mechanical. Okay, it's going to turn into things like heat, sound, okay, things like that. Okay, it'll all still be there, all 5.3 joules of it. Okay, so the law of conservation of energy says energy can be converted from one form to another. It cannot be created and it cannot be destroyed. This ball got energy because I did work. I didn't create the energy. Okay, I ate food this morning and I used that to lift up the ball and do work and give it 5.3 joules worth of energy. And then when I dropped it, okay, that 5.3 joules turned from potential to kinetic. But it's always there. Okay, that's what the law of conservation of mechanical energy says. Okay, you're always going to have that energy, okay, in or conserved within the system. All right, everybody okay with that idea? Now, in the real world, does it work that perfectly? It doesn't. Energy's still conserved. It's just not all mechanical. As this ball falls through the air, I can hear it falling because of air resistance. Okay, is it losing some of its energy as it falls? It is. It's not all getting turned into kinetic. Some of it is going to be sound and heat and whatever else. Okay, that's fine. But as long as we understand that the energy is all still there. Okay. All right. Would this be true for lots of situations then, besides something as simple as this? Anybody ever ride a roller coaster before? Okay. Why do you always have to get towed to the top of the first hill? Or at least in a classic roller coaster you do. Well, you ever notice that the first hill is always the highest? There's never a hill as high as that after? Because you're giving it, the machine is doing all the work, taking the train to the top of that first hill, and then after that, it coasts. Okay, it just goes down the track. Now it's going to lose energy to heat and sound. That's why there's never another hill that's as tall as the first one. It wouldn't have enough energy to get up there. Okay, but if it was a perfect system, okay, and no energy was lost to anything else, okay, if I towed you to the top of that first hill, you'd never be able to get off. Because the thing would just keep going. Okay, it would never lose any energy. It would always convert all of its mechanical energy from potential to kinetic, and it would just keep going over and over and over again. Okay, which would be fun and not so fun, depending on how much you like rides. Okay. Okay, couple of reminders. Your lab reports for Need for Speed Lab, 8:30 a.m. tomorrow. Okay, make sure you have them done and submitted. Those work labs are due after the break. Okay, I got to put that up on the board, but it is on Google Classroom as January the 6th. Okay, I think most people got them done yesterday, but okay, submit them when you're ready. Okay. Tomorrow, we'll be looking at law of conservation of energy problems. They are the most algebraically involved questions you will do. Okay? Are they super hard? No. There's just a lot of things you have to move around. Okay.